the settings. I've closed the special app that controls the camera, and I think it interferes sometimes. Picking it up okay, I think so. All right. So let me share the review document right here. Come on. There we go. Sharing. Okay, that's good. Now, let's see. Should be enough. Okay. My chapter 5, your chapter 10. Number 1. We shouldn't have to spend too much time on these guys because they're definitional. Gases generally have what? Low density is true, right? Because there are not that many molecules in a cubic meter as compared to a solid or a liquid. High density, no. Closely packed particles, no. No increase in volume when temperature is increased. That's a lie. I mean, poor Charles, right? His law just went out the window with that one. No decrease in volume when pressure is increased. And Boyle's went out the window with that one. Right? So the only one that's good is A, low density. Pressure is what? Pressure is defined as a force per unit area. Right? Force, pressure equals force per unit area. That's a basic definition. D. D. E is the unit of pressure that is standard for the international system. That's the Pascal. Okay, now we get to a calculation. Looks like that's 5. A glass column is filled with mercury and inverted in a pool of mercury. The mercury column stabilizes at a height of 729 millimeters above the pool. What's the pressure of the atmosphere? And look at the answers. The answers are in atmospheres. So with that 729 millimeters of mercury on your barometer, as we just made it, we convert that. Right. Actually, if you want to, you can just go ahead and put 760 here. And that should be 0.959. Okay. The local weather forecaster reports that the current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmosphere? That's a similar conversion, only with a different conversion factor. 30.4 inches. 30.4 inches of mercury. All right. What's the conversion factor there? You might have to look that one up. It's in useful information. All right, so inches of mercury on the bottom and atmospheres on the top. So how many inches of mercury in one atmosphere? You can look it up. Well, it should be in your review document. Right, yep. Look at the back, useful information. There it is, useful information.
Well, inches to what? 18.
Yeah, one atmosphere equals 29.92 inches of mercury.
Oh, okay.
So it's going to be a little over 1, right? 1.02 in this case. All right.
Right.
If you divide 30 by 29, it's going to be more than 1, isn't it?
Oh, I was about to say, I think I saw it was 29. I don't think it was 1 something.
Yeah.
29.
Yeah, 29.92. All right, let's see. 8. Air pressure in the inner tube of a tire on a typical racing bike is 112 psi. 112 psi gauge pressure in that inner tube, in that racing tire. What's the atmosphere there? Dimensional analysis, psi. What did I say?
14.
Atmosphere. Yeah, 14.69 divided into that gives us 7.62 atmospheres. Right?
Gives you what?
Is that about right? 7 times 4 is 28. 2 and 7 is 9.
7.6.
Yeah.
Yeah.
Yeah. That looks good. That's 8. 9. Boyle's law states. Okay. 9. What's Boyle's law? Well, we know that P times V equals a constant. But what is it in words? Let's see. How about the volume of a fixed amount of gas is inversely proportional to the pressure at constant temperature. Fixed amount of gas means moles is constant. Constant temperature is listed there. So yeah, those two must be constant in order for P and V to vary with that inverse proportion. Is B. How about Avogadro's law? Remember Avogadro? If we write it mathematically, it's a relationship of volume to moles equals a constant. But I like the expression where Avogadro takes gases at the same pressure, pressure 1 equals pressure 2, inside these different, the volume is the same, and the temperature is the same, then the moles have to be the same. Okay, so the one that fits that bill is A, equal amounts of gases occupy the same volume at constant temperature and pressure. That speaks to this one more than it does to this one. Charles' law. What number is that? 11? 11. Charles is talking about the relationship of volume and temperature. And remember, when we do these calculations, we generally don't use that formula. We use either before and after. Temperature 1, 2, temperature 2. We usually do the before and after situation. As temperature increases, volume increases. So it looks like C would be the best one. The volume of a fixed amount of gas is directly proportional to its temperature in Kelvin. Right? And the temperature always has to be converted to Kelvin. Remember why? No negatives. Exactly right. Yeah. Okay, let's see. What's the next one I had marked off? Gaseous chlorine. Gaseous chlorine is held in 2 separate containers at identical temperature and pressure. 2 separate containers. They don't necessarily have to be the same size, the same volume, but they do have to be the same temperature and same pressure. Okay, we know that. The volume of container 1 is 1.3 liters. And with 6.7 moles of the gas. 6.7 moles of gas. The volume of the second one is 2.33 liters. And I bet the question is how many moles? Yep. So the question is how many moles are in the second one? Well, if this is volume 1 and moles 1, then volume and moles, that's Avogadro's law. So we can say volume 1 equals moles 1 over moles 1 equals volume 2 over moles 2. Now, if you have trouble remembering that one, just remember the combined law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And then if you hold the pressure and temperature constant, right, pressure goes away, temperature goes away, and you're left with volume over moles, volume over moles. So you can derive the equation you need if you know which ones are constant. In this case, we want to solve for N2, right? So N2 comes over here, and V2 combines with N1, and then V1 comes over here. We just solve for the unknown. Plug in the values. In the interest of time, I'm not going to do that. Plug in the values, and you should get 12 moles. Let's see if that makes sense. You've gone from 1.3 to 2.3, not quite twice. Not quite twice. So they're directly proportional. So the moles should be not quite twice. 6.7 to 12. That looks reasonable. Yeah, 8. And up to this point, we've only worked problems with before and after situations where you have conditions. You're given absolute conditions here and then there, and then absolute condition here, and they're missing on the other side. So that's a before and after problem solution. All right, this may take a little bit. 18. Body temperature is 309 K. So let's say your temperature, let's say temperature 1 is 309 K. On a cold day, what volume of air at 276 K? So T2 is a different temperature, 276 K. Right, that's outside your body. This is inside your body. What volume is associated with this one? With a lung capacity of 2.2 liters. The lung capacity would be at that temperature. That volume would be 2.20 liters. What they're asking is, how much of air at this temperature do you need to draw in to fill that volume at this temperature? Right? So this second volume is the volume at the outside temperature. All right? So we can use this formula again, volume and temperature, volume and temperature. This is going to, the pressure is going to be the same because it's all at 1 atmosphere, right? Air outside and air inside, same pressure. And the number of moles should also be constant. We're assuming that it is constant. So temperature and volume would be Charles' law, right? Volume 1 over temperature 1 equals volume 2 over temperature 2. And we want volume 2. So we say volume 2 then is equal to bring that T2 over here, V1 T2 over T1. And the temperature is already in Kelvin, so you don't have to worry about that. And the volume units don't matter as long as they're in the answer. So V1 would be 2.2 liters. T2 equals 276 K. And T1 is 309 K. So let's see if, because none of these is an option, then we need to calculate it. 2.2 times 276 divided by 309. I get 1.9, three significant figures. 1.97 liters. Is the volume of air at this lower temperature outside your body. in order to fill your lungs at that temperature. All right. 20. All right. You got two balloons, an orange balloon and a blue balloon. An orange and I think the blue one is smaller. Blue, orange. Okay, what's in the orange balloon? The orange balloon is filled with neon, and the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. So the volume, let's see, the volume of neon balloon is related to the volume of the argon balloon. How? Well, if this is twice the volume of that one, we need to multiply that one by 2 to get this one, don't we? Okay. Oh, can you see? The box is in the way. Put it over here. Okay. Okay, now what's the question? Which of the following best represents the mass ratio? Okay. Well, if we're just looking at the two, and we assume that the temperature and pressure is the same, because pressure is going to be the same because they're balloons, right? They inflate against the same pressure. And they're together in the same room, so the temperature is the same. So we're actually talking about volume change versus moles, right? Moles of neon and moles of argon. So if this one is twice the volume of that one, this one has 2 times the moles, correct? Okay. So how much would a mole of argon weigh? Let's see. Argon is about 40 grams per mole. And neon is about what? 20? Yeah, it's about 20. Roughly grams per mole. So if this one has twice as many moles as that one, then they're going to have the same mass. Right? This has twice as many particles. Right? This one, say, let's just pick a number. Say this one has 2 moles. Then this one's going to have 4 moles, right? Because it's twice the volume. Okay, that's Avogadro. Well, if this one has that many moles at 40 grams per mole, it's 80 grams, right? Mm-hmm. This one has 4 moles at 20 grams. It's also 80 grams. They're the same mass, 1-to-1 ratio.
Argon's heavier, and it has 2 of them, and then neon's less, and it has 1.
No, it has 4. See, if this one is half the volume of that one, then it has half the number of moles of that. So this one would be 4, that'd be half, be 2 moles. It's still not registering.
I get what you're saying. I'm just saying in the problem, it says that argon has type 2, and then which is the heavier one, and the lesser one only has 1.
Wait a minute.
So it's like
the orange balloon has twice the volume of the blue. This is the orange neon. It's twice the volume of the blue. Are you reading the problem backwards?
I'm the bottom down there is what I was.
Oh, if you want, in mathematical terms, if you want the volume of this one,
yeah,
it's twice the volume of argon. Right? Argon has, let's say it's 1 liter. Then 2 times that is the volume of this one, 2 liters.
That's why I'm not understanding it. It says neon is less. So how would I don't know.
No, neon's not less.
Yeah.
Neon is equal to twice the volume of argon.
Oh, Okay, well, that was where we're going.
Yeah, there you go. It's just math. Okay, so the mass ratio is 1:1. Argon weighs twice as much, but it has half the particles. All right. 20, let's see. Skip a few, get down to this one. A gas sample is heated from minus 20 C to 57 C, and the volume is increased from 2 liters to 4.5 liters. The initial pressure is 1.4. What's the final pressure? This is a combined gas law problem, 29. And in those types of problems, it's very useful to set up a table, right? PVN. Is that right? No, PVT. Because N is constant. PVT, PVT. This is one condition, this is the other condition. And then you put your values in here so you don't stick them in the wrong place. So a gas sample is heated from minus 20 degrees C up to what? 57. Okay. And the volume is increased from 2 liters to 4.5 liters. So at this temperature, it's 2 liters. And it's increased to 4.5 liters. And it starts off at a pressure of 0.14 atmospheres, right?
So,
Then you can use this formula, right? The gas is trapped. I mean, we're not introducing any more of it, so we can throw the moles out. And now we have P1 V1 over T1 equals P2 V2 over T2. And we solve for this one. And plug these numbers in there after what? We convert to K. All right. Yeah, I mean, without working the problem out and wasting time. The answer should be 0.0811 atmospheres. The final pressure after we've done these things is 0.08 atmospheres. So it went from 0.1 to 0.08. Not quite cut in half. Yeah, 0.0811. That's E. E's the answer. Uh, 30. A sample of oxygen has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules does it contain? All right. This one doesn't give us a before and after situation. So now what are we talking about? We're talking about the ideal gas equation. Right? This is a state situation. This is what it is now. We don't know how it got there. So, how many oxygen molecules? Well, this doesn't give us oxygen molecules directly, but it does give us moles. So if we solve for moles, equals PV over RT, correct? Then the pressure is, and the R determines the units of measure. Right? So we have this one, R is 0.08206 liter atmospheres per mole K. That means the temperature has to be in K, 27 plus 273. 300 K. Okay. Pressure. 800 torr, which is 800 millimeters of mercury. So we need 800 divided by 760 to give us atmospheres, because of that right there. So we just put it in like this, 800 divided by 760 is atmospheres for pressure. And then volume has to be in liters. And it is 1.72 liters. Okay. Now this will give us moles. It won't give us molecules yet. Let's see, 800, 760 divide, okay, then times 1.72 divided by 0.08206 and divided by 300. And this is 7.35 times 10 to the minus 2 moles. Then we want to convert that to molecules with Avogadro's number. 6.022 times 10 to the 23rd. And let's see, round it off to what? 3 significant figures, I think. 4.43 times 10 to the 22 molecules of oxygen. That's A. Okay. All right, that was number 30. Let's scroll to the next one. We're doing on time. Good, good, good. You're going to have to leave when? Okay. 37. This is just memory. Which conditions of pressure, temperature, and moles, respectively, are most ideal? Low pressure, high temperature, and low moles. All right, so it's low, high, low. E. Yeah. E would be best. Yeah. Okay. 40. 41.1 grams of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure at the same conditions of volume and temperature? All right. So we got 41.1 grams of neon. Excuse me. We can't work. Excuse me. We can't work from grams, so we might as well convert it to moles. Right, if we're going to talk about gases, eventually we're going to have to talk about moles. So let's just convert neon. I got a glare on that thing over there. We'll look at this one. 20.18. 20.18 grams per mole for neon. So 41.1 and 20.18 divide is 2.04 moles of neon under those conditions. Fixed volume, a given pressure. Now, what mass of argon is required to exert half the pressure? Half the pressure would be exerted by half the moles, wouldn't it? Half the pressure. So we need to work with 1.02 moles of argon. Now all we have to do is convert that back to mass. Right. It's in the neighborhood of 40, I think. Argon. 39.95. Okay. And I get 40.7 rounded off. Moles, grams of argon. E. Okay. the right. We're good. Right, 40. See if I can find one that'll stump me. For which gas are the molecules that? Oh, this one is based upon those conditions: helium, chlorine, methane, and ammonia. Helium, chlorine, methane, and ammonia. These compounds at 0 degrees and 1 atmosphere, which is standard temperature and pressure. 0 degrees C, 1 atmosphere pressure. Standard, this is STP for gases. The reason I backed up is because you don't even need to know that to answer this question. Which one's diatomic? Or chlorine, of course. But if we were to look at the others, for which gas are the collisions elastic? Well, they're all elastic, right? That's a condition of the kinetic molecular theory. All collisions are 100% elastic. In other words, there's no loss of kinetic energy on the impact. If we back up, which gas sample has the greatest number of molecules? Okay, now the greatest number of molecules would be they're all the same, right? If they're at the same temperature and pressure, and what else? Same temperature and pressure for these gases in a 1 liter flask. I left that out. They're all in a 1 liter flask, right? Same volume, pressure, temperature. They have to be the same number of moles. They're all the same for that one. I know it's not highlighted, but I couldn't resist. So that one's E. All gases are the same. How about for which gas do the molecules have the highest average velocity? Okay. If they're at the same temperature, they have the same kinetic energy. Right? So if they're at the same kinetic energy, and kinetic energy equals 1/2 mv squared, then if the mass of the molecule goes down, what happens to the velocity? It has to go up. They're inversely proportional. Okay, so the one that's moving the fastest, isn't that what it said? Highest average velocity is the lightest one. Right. Chlorine is 35-45 each, which is about 70. It's a little more than 70 actually. 12 plus 4 is 16. And this is 14 plus 3 is 17. And helium is 4. So there's your answer. That one has to be moving the fastest. That's why when you breathe helium, your voice goes up, because the waves, the sound waves, are moving faster. Increase the frequency of your voice. Which has the highest density? Well, if they're the same number of particles in the given volume, then the heaviest one will have the highest density. Chlorine. All right. Which gas has the smallest average kinetic energy? They're all the same, right? We already said that. So we can move on. 52. I know those weren't all highlighted, but it just seemed like an opportunity I couldn't pass up. 52. The mass of 1.1 liters of gas Y at STP is found to be 6.23 grams. The density gas Y is what? Grams. Mass per volume is density, right? Oh, so it's just 6.23 grams per 1.12 liters. That's the density. Mass per unit volume. And all of our answers are in grams per liter, so we know we're on the right track here. Let's see, that would be about 5 or 6. Right, closest one to that is B. All right, 53. Oh, we're going to use that same gas to answer another question. All right, same mass, same volume. The molar mass of gas Y is what? We can get density equals mass per unit volume. We can get molar mass as mass per mole. And we can also get that one, the ideal gas equation. Okay, if we take this one, we're shooting for this one right here. So if we solve this one for moles, right, it's going to be moles equals PV over RT. And if we substitute this for that, I'm sorry?
For the mass of the mole?
Yeah,
Okay.
because this is moles and that's moles, then we can substitute this expression right in there. So the molar mass is mass divided by PV over RT. And then, let's see. You know, I might be making this one harder than it needs to be. In order to calculate the molar mass, we need the number of moles and the mass. So we can calculate the number of moles here, right? What's pressure? It's 1 atmosphere, right? Standard temperature, pressure, volume of 1 liter, correct? R is 0.08206, and T is 0 degrees or 273 K, right? Right, so we can calculate the moles using that. I was making it harder than it needs to be.
Mm-hmm.
This will give us the number of moles of gas that'll fit right here. And we know the mass already. So this is 1 divided by 0.08206 and divided by 273 is 4.46 times 10 to the minus 2. So molar mass equals mass, which is 6.23. 6.23 grams. And then, what did I say? Short-term memory. 446 times 10 to the minus 2 moles. So we divide that into 6.23. And I get 100 and rounded off 140 grams per mole. Well, I went around the barn 3 or 4 times for that one. That's the wrong. I think that answer is wrong. Let me see if I calculated this right. Did anybody else do this one? Is it 1 atmosphere, 1.12 liters? That's where I made my mistake. I was thinking of a different problem. 1.12 liters. Okay, now let's do it again. 1.12 divided by 0.08206 and divided by 273 is 5.00. 5.00 times 10 to the minus 2, then 6.23. There, 125. 125. Yeah, that C is correct. The creators of this problem anticipated a mistake, just like that, where you put 1 instead of 1.12. And you came up with 140. Okay. Oh, there's the answer. I got it's the same as I've calculated, but I calculated it wrong. Yeah. Those mean old meanies. 55. All right. Argon has a density of 1.78 grams per liter at standard temperature and pressure. How many of the following gases have a density at STP greater than argon? Okay, I think we're looking at Henry Ford here. Yeah, assembly line. Chlorine, helium, ammonia, and nitrogen dioxide. We want to calculate the density of each one of those at. You know what? We may not have to calculate the density. We might be able to infer whether or not it's greater than argon. So if we put argon here, and then chlorine, helium, ammonia, and NO2. This follows from that earlier question, right? If they're all at standard temperature and pressure, then they're going to have the same number of molecules, right? So the density and the same volume, then their density is going to be based on their molar mass. So which one has the greater molar mass than argon, right? That 1.78 grams per liter is blue smoke. All they have to say is which one has a greater density than argon. Right? Well, argon is about 40, right? This one's about 70. This one's about 4. That one's about 14, and 3 is 17. And this one is 14 and 32. 46. Okay. So bigger than argon, 1, 2. That one, and that one. Yeah, so 2. C. Did you follow my reasoning?
Yeah.
Okay.
Why did the masses back there, son?
I'm sorry?
I'm good.
Okay. All right, 56. Okay, this one has stumped me in the past. I think I can manage this one. 56. Which of the following best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant temperature, constant volume? Okay, so we want a relationship between pressure and molar mass. Pressure, molar mass. Okay. I know this relationship right here. And molar mass equals mass per unit mole. So if we solve for moles and substitute that, N over here, then M over MW, like that. Then we can substitute this right here. And that gets molecular weight in the formula along with pressure. Okay? All right, let's do that. Pressure, volume equals mass and molar mass. Yeah, in RT. Okay, are there any in here that are constant? Well, let's see. The conditions were constant volume and temperature. So this one's constant, this one's constant, that one's constant. So if we put them all on the same side, then we got RT over volume, which is equal to a constant. See what I did there? I moved this one over here. And then that's the one that gets me, mass. Oh, wait a minute. 1 gram sample. Mass is constant too.
Yeah.
Right? They're all 1 gram samples. Right? So this is mass over here. Right? So if that's the case, we've got this one, and this one on top. We brought volume over here. Now we're going to take this one over here. P times molar mass equals a constant. Okay, so far?
Yeah.
What does that look like? Looks like Boyle's law. And the same shape, because you got a variable times a variable equals a constant. So if you plot them, pressure here and molar mass here, they're going to look like that. And none of them match.
But it's constant, so
What?
if it's constant, it would be easier.
What's constant?
Oh, yeah, but you said constant.
Well, it's constant temperature.
Yeah.
1 gram mass is constant.
Oh, and pressure is different.
Yeah, pressure is allowed to vary.
Okay, yeah.
How does it vary with molar mass if
Yeah.
these are constant?
How would you know the line look like that?
Because that's the way x times y equals a constant is always a hyperbola. It's always that way. Yeah. Almost got me that time. 56. All right. 58. Let me see. I need to make myself some room here. Given this reaction, and they've balanced it for us already, 2 ammonia and 3 chlorine. 2 ammonia plus 3 chlorine gas yields nitrogen and 6 hydrogen chloride. Nitrogen and 6 hydrogen chloride gas. These are all gases. Okay, if we react 5 liters of ammonia and 5 liters of chlorine, what they want to know is what's the pressure, the final pressure versus ratio with the initial pressure. This is the question. Final pressure, initial pressure. All right. There are 2 ways you can work this. You can use X as an unknown and say, all right, if we know 2 moles of that and 3 moles of this are required, then if they got equal volumes, they have equal moles. And equal moles means this one needs this. There are 3 of these for every 2 of those. So let me see. The ratio is 2 to 3 moles, but we got equal moles. So which one's going to run out first? You need more of these than you do of those, right? So chlorine's going to run out. That's the limiting factor. I'm not going to calculate the pressure first because we have equal amounts of equal volumes of each reactant. And when you have a known amount of each one of them is going to be limiting. So what we need to do is find out how many moles of each one it is, because then we can find out how much of this is produced. Okay, so I got to back up and I got to solve this equation for moles. Only, I think there's an assumption that I have to make. Standard temperature and pressure would solve for moles equals PV over RT, right? Okay. So standard pressure is 1 atmosphere. Standard volume is 22.4, I believe. No, volume is 5 liters. 5 liters. There we go. R is 0.08206. And temperature is 273, 0 degrees Celsius. Now we can calculate the number of moles of ammonia. And in fact, this will be the same number of moles of chlorine. Let me try that one again. 5.08206 divided into that and 273 divided into that. I get 0.2232 moles.
It's 0.08.
And 0.2232 moles. Okay. We know that three of these are required for every 2 of those. Right, so we're going to use up all of this. And we are assuming that the initial pressure is standard pressure, 1 atmosphere. Okay, so, well, the other way we can do it is we can, I'm sorry. Well, what we can say is, excuse me, if we use all of this up, how much of this does it take? Right, that's ammonia. And then the ratio would put ammonia down here and chlorine up here. So this is 3, this is 2. So 2 into that times 3 is 0.3347. So see, it's going to use up all of that. That's what we're saying. If this were all used up, it would need a third of a mole of chlorine, but we don't have that much. Right, so we're going to use it all up. All right, so now we have to go back and say, okay, if we're going to use all of this up, it's gone in the final pressure. And how much of these will it produce? How much nitrogen will be produced from chlorine? Well, it's 1 to 3, right? So 0.2232 entering 3 divide. This is 7.440 times 10 to the minus 2 moles of nitrogen. How many moles of hydrogen chloride would it produce? 6 times that, wouldn't it? Right. For every one of these, you get 6 of those. Okay. So times 6 equals 4.46 times 10 to the minus 1 moles of hydrogen chloride. Okay. This is the number of moles of product produced. These 2 right here. Now, we've used all of this one up in the final, but how much of the ammonia is left? Well, you take this one, 0.2232, because we're going to use all of it up. Then we find out how much ammonia. Right? This is chlorine. So we need chlorine on the bottom and ammonia on the top. And this is 3. 2/3 of that value. 0.2232 into. There. That's moles of ammonia used. How much do we have left? Well, let's see. Let's put it in standard notation. 0.1488 and subtract that from 2232. Okay. Now we got 7.44 times 10 to the minus 2 moles of ammonia. That much is left over, plus this much nitrogen and this much hydrogen chloride. So what's the total number of moles there? Let's see. Well, that's the same as this one, so it's 2 times that one, correct? Plus 0.446. So we've got standard notation would be 0.5948 moles after. What? We don't have to calculate the ratio here. Look, this ratio, according to Avogadro, this ratio is the same as the final moles divided by the initial moles.
Okay, so you don't have to do all this.
Yeah. So the final moles that it is here. So this is 0.5948. And the initial moles
Was 0.2.
2 times that, right? 0.2232 enter in 2 times is 4.446. 0.4464. Okay. So that ratio is 1.33.
Oh, my word.
Yeah, that took a while, didn't it?
Yeah, my brain is fried.
All right. Let's hope the rest of them aren't that bad. Are you still copying? Good. Okay.
I don't
Now, that's the way where you use, if you use real numbers. If you use X values, then it becomes a lot simpler. And in the worked problems, I've got it solved both ways. Yeah, over a page for that one. And the other one, let me see, how much room does it take? Well, it takes over a page too. Because there's a lot of explanation in it. Yeah. Okay, let's move on. 61. 0.72 grams of a liquid is vaporized at 110 degrees and 0.967 atmospheres. The gas occupies a volume of 5.559 liters. The empirical formula is CH2. What's the molecular formula? All right. In order to remember when we were doing empirical formula versus molecular formula, we could get the empirical formula from the percent mass composition. But in order to go from there to the molecular formula, we needed the true molar mass of the compound. So, yeah. So what we have to do is find out what that X is. And in order to do that, we need the molar mass of the compound. All right, so the molar mass is going to be whatever the mass is per moles. All right, so we're given, let's see, we're given the mass 0.72. We got that one, 0.72 grams. We need to find out how many moles does that represent. And I think we can use PV equals nRT and solve for N, PV over RT. And let's see, what's the pressure? 0.967 atmospheres. What's the volume? 0.559 liters.
Oh.
Yeah, 0.559 liters, right? We've still got the correct units, right, based on the R value. And then the temperature. 110 degrees. So 110 plus 273, right? That should give us the number of moles, and we can solve for the molecular weight, or the molar mass. Ten plus 2, 3, 5. So I get 1.720 times 10 to the minus 2 moles. So we substitute that in here. Find out what the molar mass is, which I get is 41.9 grams per mole. All right. So remember how to get the X value? You need the empirical weight. Carbon is 12.01. 2 hydrogens is 2.02. So we have 14.03. We ratio 41.9 divided by 14.03. And it gets very close to 3. That look reasonable? Yeah. 3 times 4 is 12, plus 1 is 40, 42. Okay, so X is 3. That means it's C3H6. Okay? I need to be transparent. Jessica Alba. The Fantastic Four.
Oh, yeah.
Isn't she the invisible one?
Yeah. Right, so that answers.
It was C3H6. Okay, we're going to skip a few of them here. Lots of repetition. Go down to 80. Are we? Yeah, it goes up into the hundreds, doesn't it? Okay, 80. If M is the molar mass, what I usually call MW, molecular weight. If M is the molar mass, R is a gas constant, T is the temperature, P is the pressure, which of the following expressions represents the density of a gas? Okay, this is the one where we've got density equals mass per unit volume. We've got molar mass. Well, let's use theirs M. Molar mass is mass per mole, and PV equals nRT. Then we're eventually solving for the density of the gas. We want to get to this point and have something over here. So if we solve this one for moles and put it in here, M over molar mass, and stick it in here, PV equals mass divided by molar mass times RT. And then we want to solve for mass and put it in there. So keep mass on this side and put PV. This is in the denominator here. It's in the numerator there. Okay. This is in the numerator here, so it's in the denominator on that side. and take that one and substitute it in to this one. D equals PVM over RT divided by V. This is in the denominator, that's in the numerator. This is in the denominator of the numerator, so it is PM over RT. So PM over RT is A. Okay? Little algebra. All right, 81. One way to isolate metals from their ores is to react the metal oxide with carbon as shown in the following reaction. Okay, so our controlling 81. Our controlling reaction is 2. Let's see, I'm going to need more room than this. Put it over here. 2MO plus carbon yields the free metal 2M solid plus carbon dioxide. Okay, what are we given? If 34.08 grams of metal oxide, okay, reacts with the excess carbon, yep, and 4.37 liters of carbon dioxide is formed. 4.37 liters is formed at what condition? 100 degrees Celsius. So that's 373 K, isn't it? And 1.50 atmosphere. Okay, identify the metal. Well, we're not given any information about that metal right there. So we can't do a direct calculation of its molar mass to find out what it is. Right? We definitely can't get it to protons, the atomic number. But maybe we can work our way around to the molar mass somehow. We're going to have to attack it from this angle. That's the number of grams. How many moles of that? Well, if we can find out how many moles of this, we can use that ratio to find out how many moles of that and determine the molar mass of MO. Okay, so let's try that. PV equals nRT, solve for moles, is PV over RT. Pressure is 1.5 atmospheres. Volume is 4.37 liters. R is 08206. And temperature is 373. Okay, so let's find out how many moles of carbon dioxide were produced. And 0.08206 divided and 373. Right. Okay, so this is 0.2142 moles of CO2. Now we can find out how many moles of MO that represents. Okay, CO2 on the bottom, MO on the top. So this is 1, that's 2. So 2 times that value is 0.4283 moles of MO. All right, so we can do the molar mass of MO, which is grams, 34.08 grams per 0.4283 moles. All right, so let's do that calculation. 34.08, flip it and divide. 79.57 grams per mole. All right, here's the trick. How do you get the molar mass of a compound if you know the molar mass of its constituents? Just add them up, right? So this is the sum of oxygen plus the metal. So if we subtract the oxygen out of it, which is 16, right? Then we have the molar mass of the metal, correct? I don't hear any objections. 57 here. This is 3, and this is 63.57 grams per mole for the metal. So we go over and look it up. No, that's too blurry. Let's see. The nearest one I can find is copper. Right? Yeah, C. All right, 82 and 83 are memorized. Standard temperature for gases is 0 degrees Celsius. Standard pressure is 1 atmosphere. '86. You're doing. Okay. Oh, all right. You want to?
I'll watch the video.
Okay. Okay.
Thank you.
All right. Who are you going to see?
My dad's family was out of town, so I'm actually gonna go see them and go next week again, because we're not gonna have class either.
Oh, I heard you were going to a concert.
I'm going, and I'm going to my dad.
Oh, okay.
Yeah. They live in Tennessee, so it's on. Yeah.
Where in Tennessee?
I live in Jefferson City.
Jefferson City.
Yeah, it's like right near Morristown.
Morristown?
Mm-hmm.
Is that up in the wedge? Is it further west?
About 3 hours away from here.
Okay. Before you get to Knoxville?
It's like 20 minutes from Knoxville. Yeah.
Okay.
It's on the way.
I got a general idea where that is. I was born in Knoxville.
Oh, really?
Yeah. Oh, UT.
Yeah.
You have to wear orange. Okay, 86. 142 milliliter sample of gas is collected over water at 22 degrees and 753 torr. What's the volume of the gas at standard temperature and pressure? When you collect gas over water, what does that mean? Did I show you guys that trick? When you have a vat of water like this, and then you have an inverted graduated cylinder, and it's marked in volume. You fill it up with water, and then you hold your hand over it and submerge it in the water, and it'll stay there until the water will stay up here until you replace it with something. So what we do is we have a reaction vessel over here, like this, and the gas that's produced is bubbled in here, and it fills that space, and we can measure the volume of the gas under those conditions. Well, when you bubble something through water, gas like that, it picks up some of the water vapor. So if you want to know anything about the water vapor the gas without the water vapor, you've got to know what's the vapor pressure of water at that given temperature. And that's what they've given us here. At 22 degrees, it's 20 torr. You forget something?
My day.
Oh, not going very far, huh? Such a big hurry to get out of here. Okay, so 142 milliliters of gas is collected. That's the actually the gas plus water vapor is 142 milliliters. And the temperature is 22 degrees. Four? Yeah, millimeters of mercury. It's the same thing. And the pressure is 753 torr. That's the total pressure. The pressure due to water vapor dissolved in the gas is 20. So this is the total. And this is the pressure of water. And Dalton says the pressure of the gas plus the pressure of the water is equal to the total pressure. So if we subtract the pressure of the water, which is 20, from that, we get 733 torr is the pressure of the gas. 733 torr is the pressure of the dry gas. Okay. All right. What's the volume of the dry gas at STP? Well, it's not 142 milliliters. The volume of the dry gas, we would need to calculate it. Like E equals nRT. And we're calculating the volume. So nRT over P. Right? Wait a minute. I'm making this harder than it needs to be. It's a ratio, isn't it? The volume of the dry gas is, yeah, it's ratio to, let's see. Yeah, the pressure. So 733 over 753 times 142. That ratio, 733 or 753, yeah, should be the volume of the dry gas. One 138 milliliters. And it's not there. I was almost making it more difficult than it needs to be again. It's not like, you seen the movie Color Purple? But with Whoopi Goldberg. Oh, you need to. It's a good one. I was going to make a reference to it, but now why bother? It's set in the South, and the two sisters are separated by their stepfather. Their stepfather, let's see, had incest with the older daughter, which is Whoopi Goldberg, and she had two children that were adopted out. And her little sister, was in danger also. And this other black farmer, and they're all black, of course, this other black farmer wanted the younger sister, but her stepfather wouldn't let her go. He says, you got to marry the older one. But his former wife had died, so he needed somebody to take care of his kids and the house. So Whoopi Goldberg got married off to him, and he was abusive. But she was always wondering what happened to her children. Eventually, they got reunited. But when she finally left her husband, she started her own business in town, and it was making pants. She was a seamstress. She made pants, one size fits all. Just they don't believe her. You don't believe me. One size fits all. Just go try them on. Every person that went in there and tried on her pants, they all fit. You know, and that's what I was going to say. One size fit all.
No.
Yeah, it was Whoopi Goldberg's first movie, and director was Steven Spielberg. I got Academy Awards for it. Huh? The Help. Yeah, I don't know about that. She hasn't done movies in a while. She's been on that talk show. That's right, talk show. Okay, 88. If you get a chance, watch it. Good movie. Oxygen gas generated by this reaction. So it's a decomposition of potassium chlorate. Solid. And it decomposes into potassium chloride plus oxygen, right? 3 oxygens. And 2 of these. Yep. This is a gas. All right, what about it? It's collected over water at 27 degrees in a 1.55 liter vessel at a total pressure of 1 atmosphere. The vapor pressure of water at 27 degrees is 26 torr. How many moles of KClO3 were consumed in the reaction? All right, we're given conditions. Temperature is 27 degrees Celsius plus 273. I know we're probably going to need that. So it's 300, right? Okay. And the pressure, the volume of the vessel is 1.55 liters. And the pressure is total pressure, 1 atmosphere. This is total pressure, is 1 atmosphere. The pressure of water vapor at that temperature is 26 torr. So the pressure of the oxygen is 760 torr, which is 1 atmosphere, 760 millimeters of mercury. 26 equals 734, right? 4. Okay. So this is divided by 760 would be atmospheres again. 734, 760 is 0.9658. 9658 atmospheres. Atmospheres, volume, temperature, we can find moles. And that'll give us the moles of oxygen. So PV equals nRT, and N equals PV over RT. Pressure is not 1 atmosphere, 0.9658. Volume is 1.55 liter. And R 0.08206. Right, too small one. And temperature is 300. So that's the moles of oxygen that were produced from that decomposition. One 1.55 times that, 0.08206 divided into it, 300 divided by that. So that's 6.08 6.08 times 10 to the minus 2 moles of oxygen. We want to convert that to moles of potassium chlorate. So the ratio oxygen to potassium chlorate is 3 oxygens and 2 potassium chlorate. So 2 times this divided by 3 is 4.05 times 10 to the minus 2 moles of potassium chlorate. Right. The question was, how many moles? Well, there it is. Oh, standard notation. Right. 0.0405 C. 0.0405 would be standard notation. Okay. 88. Okay, I got 35 minutes. Am I going to make it? No. Oh, this is a good one. 94. This combines two laws. We've got a bulb that's 2 liters and a bulb that's 3 liters. Got a big bulb here that's 3 liters and connected by a valve to another bulb that's only 2 liters. Okay. The 2-liter bulb has 1.80 atmosphere. I can't see the rest of that. Yeah. 1.80 atmospheres of gas in here. And they're separated by that valve at this point. And the 3-liter one has 3 atmosphere pressure. All right. Question is, what's the final pressure when we open that valve and let it mix? Well, semi-quantitatively, where it's going to be. If this one's at 3 atmospheres and this is 1.8, the pressure is going to be somewhere in between that, isn't it? Right? It won't be as low. It won't be below 1.8. It won't be above 3. But what we have to do is decide, how do we get at the pressure? Well, remember Dalton said that the total pressure equals the pressure of the 2-liter plus the pressure of the 3-liter, contributed by these two. Well, how do we do that? How do we get at that? Well, what we have to do is say, what would the pressure be if that were a vacuum? And that would be the pressure contribution from this side. Then we say, what would the pressure be if that were a vacuum? That would be the contribution from this one, then add together. So, let's see. P1, V1, P2, V2. For this side, the initial volume is 3 liters. Initial pressure is 3 atmospheres. The final pressure is unknown. And the final volume is what? 5 liters. 3 plus 2. Okay. So, if P1 V1 equals P2 V2, then P2 equals P1 V1 over V2. So now all we have to do is substitute the values. So 3 for P1, 3 for V1, and V2 is 5. So 9/5, whatever that is. And 5, the 1.5 into 40 is 8. 1.80, right? Is that right? What's 9/5? Yeah, 1.80 atmospheres from this side. Now, from the other side, P1, V1, P2, V2, this was our unknown. The initial pressure on this side is 1.80 atmospheres. Initial volume is 2 liters. And the final volume is still 5 liters. So now, if we go P2 equals P1, 1.80, and V1, which is 2, divided by 5, what's that? Let's see, I'm not going to try doing that one in my head. I'm sorry? Oh. Is 0.72. 0.72 is contributed from this side. So the total pressure is going to be 1.80 plus 0.72. Right? So that's 2 here, that's 5 there, and 2.52 atmospheres, which is C.
I like this thing here.
Yeah. All right, that was 94. All right, what's next? 95. 95. All right. Partial pressures of methane, nitrogen, oxygen, and a sample of gas were found to be 135, 508, and 571, respectively. What's the mole fraction of nitrogen? Right. If we know the partial pressures of each one of these, say methane was 135. This is in millimeters of mercury. They're all same units of measure. 508 for nitrogen and 571 for oxygen. What's the mole fraction? Well, the mole fraction is proportional to the pressure. The number of moles determines the pressure. Right, you want this one right here, nitrogen, 508, divided by the sum. That'll be your mole fraction. Right? If I do my math right, it should be 0.418. Right? It's a dimensionless number. It's a fraction. It's just a fraction number because these units are canceled by those units. So it's just a fraction. We have to know its origin in order to say what it is. Dalton's law of partial pressures. All right, we've been using that one. The total pressure is equal to the summation, the arithmetic summation of the partial pressures of each of the gases in the mixture, which is D. All right. Now we get into some more math. Yeah, this chapter is heavy into math. All right, what's the root mean square velocity for oxygen molecules in a sample of oxygen at 11.8 degrees Celsius? Right. So we need, look it up, or root mean velocity. Let's see, what do they use? They use a U, I think, or mu there, R in S, something like that. It's the square root of 3 RT divided by the molar mass. Okay, so we need to know, and in this case, 2 things are important. R is not the 0.080206. This is the one that has joules in it. So we have 3 times 8.3145. joules per mole K. Okay, and then temperature does have to be in K still, which would be 11.8 plus 273. Okay, what's the molecular weight of oxygen? Diatomic gas, 16 times 2. 32 grams per mole. But joules is based upon SI units. And the SI unit for mass is not grams, it's kilograms. No, that's pounds. We want kilograms. Right? If you want to change it like this, we can do it like that. Get rid of grams, right? Numerator, denominator, kilograms here, right? So we have 10 to the third grams per kilogram. So it'd be 32 times 10 to the third kilograms. Or if we move this one over one, it'd be 3.2 times 10 to the fourth kilograms per mole. 10, excuse me, that's wrong. This in the denominator. It's a minus 3. 32 minus 3, move the decimal, it's minus 2. Correct? Or if you want to just save yourself some trouble, your calculator will accept 32 times 10 to the minus 3. Then if we do that calculation, the root mean square velocity should be 471.2. 0.2 meters per second. Oops. Okay. All right, that was 103. Excuse me. 109. All right. Which of the following is included as a postulate in the kinetic molecular theory of an ideal gas? The distance between gas molecules is small compared with the size. It's just the other way around. The distance between molecules compared to their size is massive. It's huge. Lots of empty space. B, all collisions between molecules are elastic. That's true. C, in an average collision between molecules, both molecules have the same kinetic energy. No. The average kinetic energy of the gas is the same, right, represented by temperature. But the spread of kinetic energy is numbers of molecules versus the kinetic energy is actually something like this. Most of them are in here. Okay, so that's false. All molecules move randomly in zigzag directions. We don't know how they move. We do know they move randomly, right? We have to assume that, but we don't know if it's zigzag. All molecules have the same velocity. Nope, sorry. Never going to happen. B is the answer. Graham's law. Remember Graham's law? What does Graham's law talk about? Diffusion of gas molecules, right? The higher the molecular weight, the slower they move. Okay, so the one that comes closest to that is E. The rate of effusion of gases are inversely proportional to the square roots of their molar masses. Right. And I think the formula is in there in your useful information if you need it. All right, 116. You might make it. Hydrogen and chlorine gases react to form HCl. You and a friend are on opposite sides of the long hallway. You with the hydrogen, your friend with the chlorine. You both want to form HCl in the middle of the room. What's the following? Which of the following is true? Okay, I need to draw a picture. So we got a room here. Let's say it's a long, narrow room. We live in a trailer. And you got me at one end with my what? You with hydrogen. I've got the hydrogen. And my friend has the chlorine. We're going to release them. Okay, from the looks of the answers, you should release hydrogen first. Your friend should release hydrogen first. What we want to do is say, all right, which one's going to move faster? Hydrogen, right? Right, this is about 70 grams per mole. This one's about 2. Okay, so this one's going to move faster. So who needs to release first? If we're going to form hydrogen chloride in exactly the middle of the room. Yeah, the chlorine needs to go first. So your friend should release chlorine first. B. All right. So we're still talking about diffusion rates with 117. But what we want to do is put these in order of rate of diffusion. So increasing rate of diffusion. All right. So the slowest one on the left, the fastest one on the right, and everybody else in between. So we say we've got fluorine, yep, NO2, and methane. Okay. An estimate of their molar masses will do here. Right? The lightest one is going to move the fastest, have the highest rate of diffusion. So this is 19 times 2 is 38. Chlorine is about 70. Actually, it's a little bit over 70. 14 plus 16 is what? 30? Yeah, 30. And 14 plus 32 is 42, right? And this one is 12 plus 4 is 16. Okay.
14 plus
Excuse me.
32.
14 plus 52, isn't it? 14 plus, no, it's 42. Right. 2 times 16 is 32, and then 14 is 46. Excuse me. There you go. Okay, now we're ready to put them in order of, let's see, increasing rate of diffusion. So the slowest one is going to be chlorine. Slowest rate of diffusion. The next one's going to be NO2. The next one's going to be F2. And then NO. And then methane. So that should be A. One 18. Complete the following. Because real gas particles have attraction for one another. A, real gases act most ideally at STP. Well, that's a reasonable assumption, right? We said standard temperature and pressure is temperature needs to be high, right? So 0 degrees Celsius is 273 degrees above absolute zero, which is reasonable. Pressure needs to be low. 1 atmosphere is kind of low. So that's a reasonable answer, but maybe there's a better one. We assume gas particles have negligible volume. We assume gas particles. What does that have to do with attraction? Nothing really. 1 mole of an ideal gas at STP has a volume. That didn't have anything to do with it either. Real gases act more ideally at higher temperatures and lower pressures. That's a better expression. You could argue at least 2 of the above statements correctly complete the statement. You could say E. Right? D is the best answer, but you could make an argument for A and D. $124. Marker's finally given out on me. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? So in this one, we have to look at polarity. Right? Have we talked about polarity? Good. Okay. So we've got hydrogen, which is like that. We've got chlorine, which is like that. We've got ammonia, which is like that. It has a dipole like this. These are nonpolar. Ammonia is polar. And oxygen is like that. And this has the complete octet around here. Okay, so we know that the lowest van der Waals correction would not be ammonia. Right? It's polar. There's going to be a strong attraction among ammonia molecules. So what we have to do is say, with these nonpolar ones, what's the factor that influences instantaneous polarities? The primary factor is the size. The bigger ones are able to have instantaneous redistribution of electron density more easily. Right? So the biggest one would be this one. Right? So it would be the next one in line from ammonia as least ideal. The most ideal would be the smallest one, which would be hydrogen. We'll talk a whole lot more about that in the second semester. We jump right into it in the first lecture, I think. Okay, 132. Almost there. Manometer. What is a manometer? A device for measuring manhood. No, manometer is an application of a barometer. Actually, in this example, we're using Robert Boyle's J tube. Right, so this manometer is attached to a gas supply. Got a J tube here, open to the atmosphere, right, and it's connected to a gas supply that has a certain pressure in it. Okay. It occupies a volume of 2.34 liters. Maybe we need that, maybe we don't. The mercury level in the arm of the manometer attached to the gas supply on this side is 24.3 torr, or millimeters of mercury, lower than that on the arm in the open atmosphere. So this one's down here, this one's up here. Okay, and the difference is 24.3, is it? Yeah, 24.3 torr. Okay, what else are we given? Atmospheric pressure is 1.23 atmospheres. So here is 1.23 atmospheres. How many torr is that? Well, times 760. Let's go ahead and calculate it. Really? We do that again. Yep, 935. Or 34.8, let's do that. Because this one has a decimal in it too. 4. That's bearing down here. Okay. So what's the pressure inside here? Well, you've got this pressure bearing down here. How much pressure is bearing down on the gas? It's this difference, mercury. This much mercury up here is pressing down on the gas, plus what's on top of it. So that plus 24.3 is the total pressure. Let's say 959 torr is actually the pressure inside that container. E is the answer. Okay, that's why I like to draw pictures. The wording there can be confusing. That's it.